Welcome to the deep dive. So today we're going to tackle, well, maybe one of the biggest topics out there, commercial nuclear fusion.
Right, the technology of the future, the one that's always 30 years away.
And always will be, that's the old joke, but the stakes are just, you can't overstate them.
You really can't. If we get this right, if we actually achieve commercial fusion, we unlock virtually unlimited clean energy. It's a civilization level change.
Like the agricultural revolution or the industrial revolution,
Yeah.
right? It's all about energy.
Exactly, a new, denser energy source. And that's our mission today, to unpack this. We're going to focus on one company, Helion Energy, because their approach is, well, it's pretty novel and suggests we might actually get there.
Okay, so before we dive into helium specifically, let's just level set for everyone. Fusion versus fission. They sound similar, but they're polar opposites.
Complete opposites. Fission is what we have now in nuclear power plants. It's about splitting things apart.
Taking heavy atoms like uranium and breaking them.
Precisely. You split them, and you get a release of energy. Fusion, like what happens in the sun, is joining things together.
Fusing light atoms.
Fusing light atoms, like hydrogen isotopes, to make a slightly heavier one. And in both cases, the famous E=mc² is at play.
Right. The resulting stuff is just a tiny bit lighter than what you started with.
And that missing mass, the mass defect, is converted into a huge amount of energy. It's fascinating, too, that this only works up to iron.
What do you mean?
Lighter than iron, you get energy by fusion. Heavier than iron, you get energy by fission, by breaking them apart. Iron's the barrier.
Okay, so the fuel source seems like a huge difference right off the bat. Fission needs uranium, something we have to dig up.
And it's finite. Fusion fuel, specifically deuterium, is, well, it's everywhere.
Everywhere.
It's a hydrogen isotope that's in all water, heavy water. The estimates are that there's enough deuterium in the Earth's oceans to power humanity for.
For how long?
Anywhere from 100 million to a billion years at our current usage rates.
A billion years. That just removes all the geopolitical tension around energy, doesn't it?
Completely. But it leads to the big question. If the fuel is everywhere, why has fusion been so hard for 70 years?
Well, fission has been working for decades.
Because, from a physics standpoint, fission is relatively easy. You can do it at room temperature. Fusion is hard. You're literally fighting nature.
Fighting nature how?
You're fighting the electromagnetic force. You have these positively charged particles.
And charges repel.
Exactly. They repel each other intensely. So to get them close enough for the other force, the strong nuclear force, to grab them and fuse them, you have to smash them together.
And that means speed, which means heat.
A ridiculous amount of heat. Over 100 million degrees Celsius. That's what we're talking about.
Wow. Okay, so that brings us to safety. When you say nuclear, people get nervous.
And they should. But this is where the physics is, again, completely different. Fission is a self-sustaining chain reaction. That's why we call them reactors.
If something goes wrong, it's designed to keep going.
Right. Fusion isn't a chain reaction. It's more of a continuously sustained event. It's better to call it a generator.
So if you lose power or the containment field fails.
It just stops. Instantly, it cools down. In fact, a system like Helion's only has about 1 second's worth of fuel inside it at any time.
Just 1 second.
That's it. You cut off the fuel, the reaction is over. There's zero possibility of a meltdown.
That's a fundamental difference. But there's still radiation involved, right? You have 100 million degree plasma.
Oh, absolutely. During operation, you get neutrons, X-rays. You need serious shielding, concrete, things like that. But the waste product is the key.
It's not the same as fission waste.
Not at all. It's not the long-lived radioactive material you have to bury for thousands of years. It's much shorter-lived, less toxic, and a huge point for global security.
No proliferation risk.
Zero. You cannot make weapon materials from a fusion power plant. Proliferation experts are very clear on this.
Okay, so let's get into the helium tech. The big problem has always been containment. We hear about tokamaks and stellarators.
The big magnetic donuts.
Right, those are all about long confinement, holding the plasma steady for as long as possible. Helion's approach is totally different.
Completely. They use something called pulsed magneto-inertial fusion. And it's in a linear machine, not a donut.
Okay, pulsed. What does that mean?
It means they're doing everything incredibly fast. They use these advanced semiconductor switches to reverse the external magnetic field in microseconds.
Millionths of a second.
Yeah, it's like a magnetic slam. And the plasma, because it's conductive, resists that change.
So what happens to it?
It sort of folds in on itself and creates its own self-contained magnetic bubble. It's a structure called a field reversed configuration, or FRC. The plasma literally traps itself.
Wait, the plasma traps itself?
In a way, yeah, it self-organizes. Its own inertia and its own generated field hold it together.
But that sounds unstable, like balancing a spinning top. I've read FRCs are notoriously wobbly.
That is the core physics challenge they had to solve. You're right. These are high beta plasmas, meaning the particle pressure inside is almost as strong as the magnetic pressure outside. They want to tilt and fall apart.
So how do you stabilize something that's inherently unstable?
You spin it faster, metaphorically, you drive it incredibly hot, and you make it long enough. The stability is related to its temperature and its shape. The hotter it gets, the more stable it becomes during that short pulse.
And the reward for all that complexity is the power scaling, right? This is a key point in the sources.
This is the economic game changer. Fusion power output scales with the magnetic field to the 3.77 power.
So if you double the magnetic field,
You get nearly 15 times the power output.
15 times.
Exactly. And because Helion system is pulsed, they can hit much higher magnetic fields for a microsecond than a steady-state system like a tokamak ever could. That's how you get a smaller, cheaper generator.
Okay, reaction is going, but now you have to get the electricity out. And this is where they ditch the steam turbine.
Yes. This is maybe the most elegant part of the design. It's tied to their fuel choice, deuterium and helium-3.
Not the more common deuterium tritium.
Right. DT is easier to fuse, but it mostly makes uncharged neutrons. Neutrons escape, create heat, you boil water, and you're stuck at, like, 35% efficiency.
But DH3 makes something else.
It makes charged protons. And because they're charged, they're trapped by the magnetic field. So when the pulse ends and the plasma expands,
The charged particles push back.
they push back hard on the magnetic field, and that push induces a current directly in the coils. It's a linear generator.
So you're not boiling water, you're just directly capturing the expansion.
You are. And the numbers are just revolutionary. You can recover 95% of the input magnetic energy and convert the new fusion energy with 85% efficiency.
I have to ask, though, helium-3 is incredibly rare on Earth, isn't it? That's always been the knock against this fuel cycle.
It is. That's a fair point. But Helion's approach is clever. They actually create the helium-3 they need inside the machine from side reactions between the deuterium ions.
So it's a closed loop. They breed their own fuel.
Over time, yeah, it becomes a closed system. And that efficiency gain is what allows them to build something small and, manufacturable.
Which gets to the cost. At the end of the day, it's about steel, concrete, and copper.
Exactly. And that's why they have this builder-first mentality. They've built 7 prototypes already.
The ones named after Starbucks sizes, right? Trento was the last one.
That's the one. And it shows they're treating it like a product, not a giant science experiment. There was that anecdote about the turbomolecular pumps.
Oh, right. The lead time was 9 months.
So they just went on eBay and bought used ones to save time.
That's a startup mindset, not a national lab mindset.
It's about speed. And that speed has led to a very, very ambitious deadline.
The Microsoft contract, they're supposed to deliver fusion power to the grid by 2028.
I mean, that is incredibly aggressive. But it shows you where the demand is. These pulse generators can ramp up and down, which is perfect for the huge, concentrated power needs of data centers and AI.
So, if we zoom out again, if this is successful, it's not just clean energy, it's the end of energy scarcity as a driver of global conflict.
It's a fundamental change to the human equation. It's how we get to be a Kardashev Type One civilization, using all the energy available on our planet.
Which always brings me back to that really big question, the Fermi paradox. If a technology like this is possible, this kind of leap, where is everybody else?
Right. Why is the universe so quiet? And maybe the assumption that advanced civilizations expand physically is, well, maybe it's wrong.
You mean they don't go out and colonize the stars?
Maybe not. The sources bring up this idea of the Matryoshka brain.
Tell us about that.
It's the concept that a civilization might use its vast energy resources from fusion or, say, surrounding their star, not for travel, but for computation.
For thinking.
For thinking. For creating immense nested layers of computing to achieve some kind of ultra-advanced intelligence. They expand into consciousness, not into space.
So the final thought for you to take away from this is the ultimate destination for humanity expansion into space and time? Or is it an expansion inward, using all this energy from fusion to power and explosion of intellect and consciousness? Maybe the aliens just aren't answering because they're too busy thinking.